This lecture is in the continuation of the previous lecture where we have discussed about the big O notation and we have seen some examples related to big O notation. Here also we will see some examples related to big O notation, but we will also summarize what we have learned so far in asymptotic analysis. So let's get started. We are always interested in finding the growth rate of the function, isn't that so? We will take one function under consideration and we used to compare it with the size of the input. So as size of the input grows, how our function grows, we need to know that. For this purpose, we plug in different values of n into the function. N is basically representing the size of the input. We basically plug in different values of n into the function and plot a graph to know the growth rate of the function. But why do we need to do this? Why we need to find the growth rate of the function? Why is it so important? Let's see this why it is so important. Let's say we are comparing two data structures for a particular operation, okay? It might be possible that for some set of inputs, first data structure may give the best results. It might be possible that for some set of inputs, first data structure may give the best results, while for some other set of inputs, second data structure may give the best results. This can be the possibility. We can't simply predict that after which value of n, we can be sure that the one data structure will perform better than the other data structure. If you can't simply understand what I'm saying, then please see this graph. Here you can see that for n less than or equal to 3, Gn is performing better than Fn. Isn't that so? Fn is actually growing faster than Gn. But for n greater than 3, Gn is growing faster than Fn. You can clearly see that n is equal to 3 is the point after which we can be sure that Gn is growing faster than Fn. Isn't that so? Or in other words, I can say that Fn is performing better than Gn. So the value of n is very important here in this case. After that, we can be sure that which function is performing better than the other function. This is the reason why we are plugging in different values of n and are interested in the growth rate of the functions, representing the time taken by the operations performed on data structures. Because we are talking about data structures here, so we are considering the function as the time taken by the operations performed on data structures. Okay? But isn't it a tedious task to plug in different values of n and find the growth rate of the functions for comparison purpose? Obviously, it is a tedious task. You need to plug in different values of n. You need to determine the growth rate of the function. It might be possible that for n equals to 10,000, you will get that point that after which you can be sure that which data structure is performing better. It is very tedious task. Now here comes the big O notation to rescue. Big O notation helps us in finding the growth rate of the function without plugging in different values of n. That is the beauty of big O notation. Here we need not to plug in different values of n into the function in order to determine the growth rate of the function. Big O notation is the tool to find the growth rate of the function without plugging in different values of the size of the input. And the best part is it gives the least upper bound on the function, which gives the surety that the function under consideration will never grow faster than this upper bound. So what it gives the least upper bound on the function. Let's say the function under consideration is f. The least upper bound is g. So with this upper bound, we will be sure that g is always greater than f. Or in other words, I can say that g grows faster than f. With this, we can be sure that the function under consideration will never grow faster than this upper bound because the upper bound always grows faster than the function under consideration. So we can think of that least upper bound as the worst case time complexity of the algorithm. So the time complexity which we are considering is f of the algorithm, but the least upper bound, which is represented by g, tells how worst an algorithm can perform. So basically this is the upper bound which tells how worst an algorithm can perform. Let's see one example here. Here we have fn is equals to 5n square plus 4 and gn is equals to n square. Okay, we need to determine is fn is equals to big O of gn. That means we need to determine is gn is the least upper bound on fn. For this purpose, obviously we need to compare fn and gn like this. Fn less than or equal to c dot gn. If you want to know is fn is equals to big O of gn, then according to the definition, we need to compare these two fn and gn by using this inequality. Now let's take c equals to 6 and let's plug in the values of fn and gn here. We will get 5n square plus 4 less than or equal to 6 into n square. We are taking c equals to 6. Obviously we need to determine this constant, right? So we have taken it 6 because this is 5n square. This is just n square. If you put one greater value here, it might be possible that gn becomes greater than fn. Right now gn is not greater than fn, right? After this, we need to determine the value of n. For this purpose, we will solve this equation. N square becomes greater than or equal to 4, and then after that, n becomes greater than or equal to 2. So it is clear from this inequality that Fn is less than or equal to c dot gn for all n greater than or equal to 2. Here n naught is equals to 2, where c is equals to 6 and n naught is equals to 2. Here you can see the n naught value is 2 and c, that is the constant, is 6. So with these constants, we will get that Fn is less than or equal to c dot gn. Here gn is representing the least upper bound on Fn. So what we can say about this function? Fn is equals to big O of n square, which means that our function grows quadratically. So we can say that the growth rate of this function is quadratic. So this gn is basically representing the upper bound on Fn, that is the worst case time complexity. This function will never grow faster than quadratic. It is not the case that it suddenly grows like, a cubic function. In the worst case, this is the time complexity, that is quadratic growth. Okay? Big O notation is simplifying the task, isn't that so? It eliminates all the unnecessary terms from the function which are not contributing much in the overall running time. In the previous example, you can see that constant 4 is not contributing much to the time, it's just a constant. While that n square is contributing much of the time. That is why big O of n square we get. So it eliminates all the unnecessary terms from the function which are not contributing much in the overall running time. Now, let's consider some growth rate of the standard functions. Here you can see these are some standard functions and here are their growth rates. Here you can see the values of n, that is 1, 2, 4, 8, 16, 32. You can clearly see that log n base 2 has the least growth while 2 to the power n has exponential growth. You can clearly see over here the value is 4 to 9 into 10 to the power 7 for n equal to 32. Here it is just 5. So we can compare these functions obviously. Basically we use these standard functions for least upper bound on a particular function under consideration. So we usually put them in place of gn. We can use log n base 2, n log n base 2, n square, n cube, 2 to the power n. These are different functions available which are also known as standard functions. Now let's consider one programming example which helps us in understanding how big O notation works in reality. Here you can see this program is used to calculate the sum of first n natural numbers. Within this main function I have declared 3 variables I, sum and n. After that I have a scanf function which is used to ask input from the user, that is n. After that we have this for loop and we will run this for loop from 1 to n. That means total n times, right? Here within this for loop we can see that one statement is there, sum equals to sum plus I. After this for loop completes, sum contains the sum of first n natural numbers, isn't that so? Then we will simply print that sum on the screen. You can clearly say that first term is executed just one time, scanf is executed one time, this statement execute n times because this statement is within this for loop. This for loop runs from 1 to n, which means that this statement is executed n times. This statement just takes one time, this statement is executed one time and this statement also executed one time. Let's add them all up. This gives us Fn equals to n plus 4. Fn keeps the count of number of instructions, isn't that so? That's also we have learned about Fn. By keeping the count of instructions, we are calculating the runtime. That's an approximation obviously. So Fn is equals to n plus 4. Now, we know that Fn is equals to n plus 4. Let's take Gn equals to n. We are interested in finding the growth rate of this function. That's why we have taken Gn equals to n, which I thought of that as the least upper bound on Fn. Is Fn is equals to big O of Gn? That's what we need to find. For this purpose, obviously, we need to compare Fn and Gn. Here n plus 4 must be less than or equal to c dot n. We need to determine the value of c. Let's take c equals to 2. Obviously, because this is n, let's take it one higher. This will be n plus 4 less than or equal to 2 into n. Let me tell you that c value could be anything. That depends on you. I usually take one value higher than the value specified over here. So that is why I have taken c equals to 2 in this case. I'll simply compare n plus 4 with 2n. After that, what we will get is n greater than or equal to 4. So we can say that Fn is less than or equal to c dot gn for all n greater than or equal to n naught, where c is equals to 2 and n naught is equals to 4. Here you can see n naught is equals to 4, c equals to 2. For these two constants, Fn is less than or equal to c dot gn. So we can clearly say that Fn is equals to big O of n. We can also clearly see here that the growth rate can be linear only because the highest term here you can see is n. After that we have a constant term. So Fn grows linearly. That is why Fn is equals to big O of n. This is the worst case time complexity of calculating the sum of n natural numbers. But can we improve our algorithm? Let's say the program which is taking linear time is written by your friend. You need to write a program which performs better than your friend's program. For this purpose, you have written something like this. Here also, instead of running the for loop, we can simply use this formula, right? N into n plus 1 divided by 2. This will calculate the sum of first n natural numbers, isn't that so? With this simple idea, we are actually replacing the for loop. There is no involvement of loop in this code, which is actually responsible for giving the linear growth. Here, all these statements execute one time. So total fn is equals to 4. It's a constant number. There is no n in this case. Now as we know fn is equals to 4, let's take gn equals to 1. I thought of that this must be a constant. Is fn is equals to big O of gn? Fn must be less than or equal to c dot gn. For this purpose, we'll plug in the values of fn and gn. We got this 4 less than or equal to c dot 1. Let's take c equals to 5. This will be 4 less than or equal to 5. So fn is less than or equal to c dot gn for all n greater than or equal to n naught, where c is equal to 5 and n naught is equals to 1. Then definitely we can say that fn is big O of 1. That's the constant growth. So fn grows in a constant manner because this is just a constant number. 4 is just a constant. It doesn't depend on the n value. So our fn doesn't depend on the size of the input. So it is clearly the fastest algorithm among all. The algorithm written by you for calculating the sum of first n natural numbers is the fastest among all. Your friend has written an algorithm which has a linear growth. You have written an algorithm which has constant growth. So your algorithm runs faster than his algorithm. In this way, big O notation is very useful in determining the growth rate of the function. Not only that, it gives the worst case time complexity of a particular algorithm. So this is the beauty of big O notation. With big O notation, we can easily identify which particular program is better than the other program. Here we are considering two different programs. One has a linear growth and the other one has a constant growth. You can clearly say that the program written by you is the best and the program which is written by your friend is not. Okay friends, this is it for now. Thank you for watching this presentation.